Hi guys, welcome to today's recording. We're going to go through the 2020 structure and bonding examination paper today. So like always, if you've been finding my channel helpful, please subscribe, leave a like, and drop me a message in the comment section if you find anything particularly difficult to understand, then I'll try to help you out. Okay, so question number one. So structure and bonding is pretty straightforward, standard, very it's quite predictable compared to organic in comparison. Like, it's quite polarizing. It's just really, most of it's from year 12, I think. The calculation isn't too difficult, but if you've been struggling, hopefully after this video you can do better. All right, so let's get started. So for this particular question, we're looking at the attractive forces between these things. So CH3Br, this has temporary dipole-dipole force of attraction, as well as permanent dipole-dipole force of attraction, because this is a polar molecule. Br2 only has temporary dipole-dipole force of attraction because it's non-polar. And calcium bromide, so this is a change. Normally they just give you molecular solids, but calcium bromide, if you remember from year 12, this is an ionic solid, so this has ionic bonding. So don't get too trigger happy and just go, oh, I know, everything has temporary dipole-dipole force of attraction, and so does calcium bromide. Well, it doesn't. It's an ionic solids. Okay, now with reference to the relative strength to the attractive forces, justify the following. Calcium bromide has a higher boiling point than both bromo, methane, and bromine. So calcium bromide, so this is where you can talk about calcium bromide has ionic bonding, and the ionic bonding is between the oppositely charged ions. So this is a lot stronger compared to, this is much stronger compared to the molecular forces, intermolecular forces. If it's stronger, that means you require more energy to overcome this particular force of attraction. Okay, so this is a welcoming change, to be honest, because normally they just ask you questions about hydrogen bonding, permanent dipole-dipole, temporary dipole-dipole, but ionic bonding, this is a nice change because this is from year 12, because they are technically allowed to assess you anything from year 12 and year 13. So this is a good change. Now bromo, methane, so these guys just have intermolecular forces. You don't need to go into details to talk about what type of forces they are, because you're just comparing ionic versus intermolecular, which is weaker and therefore requiring less energy, therefore has a lower boiling point. Okay, so let's have a look at the answers. So there you go. So calcium bromide has ionic bonding, which is a lot stronger. The other one has intermolecular forces, so more heat energy is required, therefore you have a higher boiling point. All right, next one, bromine has a higher boiling point than bromomethane. So let's go back up here. Bromine 59, 3.6. Okay, so Br2, so they're saying for this one, they're saying Br2 has a larger boiling point than CH3Br, and they're like, why is that? Okay, and this is where you need to consider the strength of this particular type of intermolecular forces. Br2 only have temporary dipole-dipole force of attraction, and CH3Br has temporary dipole-dipole force of attraction, as well as permanent dipole-dipole force of attraction. So on paper you may go, oh, this has, this is a polar molecule. Polar molecule should, the permanent dipole-dipole force of attraction, between the positive ends and negative ends should be stronger than the temporary dipole-dipole, right? But it depends on the molar mass. Okay, so Br2, this has a very large molar mass. It has a very large molar mass. When you have a large molar mass, that means you have loss of electrons. When you have loss of electrons, and what is temporary dipole-dipole force of attraction again? So again, this is not a scientifically correct diagram, but you get the idea. Like say for example, if I have 10 electrons all together in any particular moment, I ended up with 8 electrons on the left hand side and then 2 electrons on the right hand side, and this is going to be slightly negative, this is going to be slightly positive, and then you form these temporary dipoles. Okay, because why is it called temporary? Because these the electrons can move around, and then next second could be 8, like could be 4 6, 5 5 3, that's 3 7, they would randomly move around. So this is temporary. But when you have a large molar mass and when you have lots of electrons, let's say instead of using 10 electrons, let's use 100 electrons. What if I have 80 electrons on the left hand side? Again, not a scientifically fully correct diagram here, but I'm just trying to get you to understand. Can you look at the ratio here? So this is 8 versus 2, this is 80 versus 20. So this difference is 6, this difference is 60. Can you see this negative is going to be a lot stronger than this delta negative because you have more electrons? All right, so the larger the molar mass, the more electrons you have. The more electrons you have, the more polarizable molecule you have. So that means you create stronger dipoles, stronger temporary dipole force of attraction, and that will require more energy. Okay, so this is nothing too new, I hope. So again, here's the answers. Answers: Br2 has a larger molar mass, larger full electron cloud, more energy is required because it's stronger than the total combination of the temporary dipole and the permanent dipole in the CH3Br molecules. Okay, because the molar mass is too big. All right. Next one, look at B. Oh, calculation. Calculate the temperature change when 1.7 grams of solid is being added into 35 grams of water. So when you see a question like this, when you see this number 4.18, this is your Q equals MC delta T. Q equals MC delta T type of question. Okay, but this time we have to work backwards. We don't know T. We don't know this one. All right, because they said calculate the temperature. So what do we know? We know Q. Do we know Q? Oh, we know here. We know this one here, 44.5 kilojoules per mole. We know 35 grams of water. We know 1.7 grams of solid sodium hydroxide. We know 36.7 grams of the sodium hydroxide mass. Sorry, the solution, not because the mass is 1.70, and then the mass is 40. The molar mass is 40 grams per mole. Now, the reason why I highlighted all the numbers is that in chemistry, this is not math or physics, but in chemistry, you tend to use every single number once, not twice. We normally you just use each individual number once. Okay, but you have to use all of them. We normally don't give you a number for no reason. Okay, like we don't give you a molar mass here for no reason, just for it to sit there look pretty, we don't do that. So we have to work backwards. So the forward way that when we start teaching, when your chem teachers start teaching, you say, all right, we do Q equals MC delta T, we find the mass of water, we find that we know the constant, we know the change of temperature, we know how much energy we're dealing with, and then we can use that to calculate the enthalpy, which is negative Q divided by the number of moles, which is kilojoules divided by moles, which is kilojoules per mole. But I already know we know that we need to calculate delta T, so we need to go backwards. So we already know quite a few numbers. Can you see the 45? Can you see this number's right there? So this is negative 44.5 equals negative Q divided by, what is this again? This is the mole. What are we going to use to figure out the mole? All right, so that's looking at, we put the sodium hydroxide into the solution, it started to give heat. So it's obviously the sodium hydroxide mole that we need to look at. So we have the molar mass, we have the mass here. So the molar mass, the mole is going to be 1.7 divided by 40. All right, and equals small m divided by big M. It's almost like again, just being very pragmatic, just hopefully you can do well in the exam, is that you normally, whenever we give you the molar mass, find the grams, use that divided by the molar mass, you get one step correct of the calculation, and normally you get something. All right, you get one step of calculation gives you one achieved tick. and you normally need about 8 or 9 to pass. So that's what, 12.5% right there. Okay, so it's 1.7 divided by 40, which is going to be 0.0425 moles. Okay, so that's going to be divided by 0.0425 moles, and then Q is going to equal to 45, 1.89 kilojoules. Okay, Q is going to be equaling to 1.89 kilojoules. Now, we know Q now, so we know this is 1.89. Now, just be very careful because we're dealing with kilojoules here, and normally the Q that we have here is calculated in joules. So this is going to be 1890 joules equals what? The mass of water, which is right here, 35 grams. Or actually, we're not going to use that. Well, you know how I said you use your number once? They kind of did it for you. You have 1.70 grams here, you add it to 35 grams here, and they told you the solution is added to 36.7. So this time, you know, they just gave you the number. They did it for you. So 36.7 times C, which is 4.18, times delta T. So delta T is calculated using 1890 divided by 36.7 divided by, multiplied by 4.18, and then you should get 12.3 degrees Celsius. Okay, so it's just math, just working backwards. Yeah, so hopefully that's not too difficult. All right, question number 2. What are we doing here? So we're looking at the heating curve. So the heating curve is something that's quite cool. Normally every year I do the practical, you know, and again, yeah, my year 13s normally just the practical. This practical is really chill. They just do it and they have a bit of fun, but you know, they don't really take too much notice of it. But this happens to be actually one of the really for last year came as a big surprise to a lot of people, because of the fact that we normally, like if you go through the past exam papers, the heating curve, it never really shows up, but it's actually quite an important concept. But just really, let's just answer the question first. All right, so write the equation for the reaction that has enthalpy change equal to the standard enthalpy of vaporization. So vaporization, vapor, so you're going from the enthalpy of vaporization is when you have something that's SbH3 going from, you know, vaporizing, so it's going from a liquid going to a gas. Okay, so that's vaporization. Fusion is when you're going from a solid to a liquid. Vaporization, going from liquid to a gas. Now, with reference to the heating curve, explain the physical changes between A and D. Your answer should refer to energy movement and particles and intermolecular forces. Okay, so this is where, you know, you start here and then you're starting to heat it, yeah, and between point A and D. Okay, so you start heating it, and then once it gets over here, this is normally when you have a solid. This is solid. It stands for solid. And during this particular section, I know it's not being asked in the question, but you know, might as well going through that for you. In this particular section, you're going through the state changes from solid to a liquid. So the heat energy, you can see the temperature is having a flat line, so the temperature is not increasing, but then the solution, this particular thing is still being heated. Where did the actual heat energy go? If it, you know, because the temperature is not rising, where did the heat energy go? The heat energy went into the solid to break the intermolecular forces to turn it into a liquid. And then when you get to A, you have a liquid now. When you get to point A, you have a liquid, and then from point A to point B, it's heating up, so it's gaining kinetic energy. That's because the temperature increases, as you can see, going from -80 to -20. From A to B, the energy is going into the solution, going to the liquid, and they're bumping around, you know, moving around, and then very excited. But when they get to B, to C, this is going from liquid to gas. Okay, so that's the enthalpy of vaporization that we talked about here. The energy is not the temperature is not increasing because the heat energy has gone into the liquid to break the intermolecular forces. Okay, so the energy has gone into the molecules to break the intermolecular forces. Hence, the temperature is not going up. And then when you finish that, when you get to C, it's turning into a gas, and then the temperature increases again because the molecules are moving around quicker. Okay, so hopefully that kind of makes sense. So just really quickly, so between A and B, the chemical gains kinetic energy, so temperature increases, all right, and then they move around quicker. Okay, so intermolecular force becomes weaker. You can think of it as they really, like, think of a bunch of children high on sugar, like they're so energetic, they don't want to sit still, they want to move around, until the certain point of the bell, boom, the bell goes, and they're like, yay, yay, run out to the playground and play. Okay, so between B and C, this is where, so just really quick here again, so this is A, B, C. I think look like that. I think A, B, C, D. I think this is what it looks like. So between A and B, they're gaining temperature, they're gaining energy. But from B and C, the heat energy is being used to break the intermolecular forces. So they are not resulting in the temperature being going up because the kinetic energy remains constant. So it's separating the molecules away from each other, and then it's because it's changing state. Okay, and between C and D, so same process, the molecules is gaining kinetic energy, therefore temperature increases, and therefore the molecules are moving faster and faster because they have more kinetic energy. So it's really kind of standard. You just have to understand that these flat lines, we normally do, like I do a practical every year with my year 13 just to show them that, it doesn't work that well, but it kind of does the trick, is that if you can actually observe this, like the temperature stays the same for a short period of time, even though you're heating it. And then it's not your thermometer being broken, it's just that the energy has gone in to break the intermolecular forces. Okay, and one of the really popular questions they always ask, why is the enthalpy of vaporization always going to be bigger than the enthalpy of fusion? Very popular merit-ish type of question. Then you just need to realize that vaporization is going from liquid to gas. This is going from solid to liquid. Liquid to gas, you've broken all intermolecular forces, whereas solid to liquid, you've broken parts, and a percentage of the intermolecular forces. Next one, that's a bit small, let's make that a little bit bigger. All right, so this thing can be blah blah blah, calculate the standard enthalpy of formation for, okay, so when you get calculations like this, I just look at these enthalpies. So this is not, you don't need the Hess's law to do this. You just go enthalpy of reaction equals the total the total of enthalpy formation of products minus the total of enthalpy of formation of reactants. Okay, so what are my products? My products is this. What are my reactants? My reactants is this. And I don't care about the oxygen because that's an element. Element has no enthalpy of formation. So what numbers do we know? We know this number is right there. So this is -1H68. Enthalpy of products. So products is going to be sp2O3. So that's going to be -720 plus 3 times -286. That's my products. And then my reactant is going to be just that, 2 times SbH3. But I don't know what that is because that's what I'm trying to figure out. And then if you solve this, you're gonna get, let me just crunch this. I'll just, 1.68 -720 plus 3 times -286. It's gonna be -1578 plus -2x. I'm just gonna use it as x. So that's going to be 2x equals to 290, and then x equals 145 kilojoules per mole. Okay, that's done. Why did I put a liter there? I'm so drunk. All right, there we go. All right, next one. Explain how the enthalpy of reaction would differ if the water produced as a gas rather than a liquid. So let's come back up here. So over here, we can see that you made a liquid, and they're simply asking you what happens if you change this. Instead of making a liquid, you are making a gas. So you have to remember, if instead of making a liquid, you want to make a gas, you have to turn the liquid to the gas. And in order for this process to happen, you need to absorb energy. All right, you need to absorb energy to make this happen. So that as a result, because you're absorbing energy to make this process happen, you release less energy. It's kind of like, you know, if you're trying to think of an example, like say if you own a business, yeah, you're making a certain amount of money, like say you're earning, I don't know, 50K per month, I don't know, that's good business. Like say if you earn 50K a month, like, but then you realize that you need to do this particular process of liquid to gas, like say you need to fix some machines, and that's going to cost you 10K, and then therefore you earn less, you earn 40K, because you have to spend some to do this actual process. Yeah, so hopefully that kind of makes sense. So yeah, that's just it's just one extra step. All right, so the enthalpy change will be less negative, because the some energy is absorbed to break the intermolecular forces to change it to liquid to gas. Therefore, you have less energy released. Okay, so it's just, you know, just get your head around it. I think with structure and bonding, it's more about just getting your head around it, and then you should be fine. Yep. All right, for C. When solid calcium is added to test tube, blah 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 blah, the rigorously becomes hot, bubbles or hydrogen gas, well, entropy change in system surrounding, y direction. Okay, so this is to do with spontaneity. Yeah. So first thing first, let's look at entropy change. Let's look at entropy change. You're going from 1 mole of solid, we're acting with 2 moles of aqueous. You're making 1 mole of aqueous and 1 mole of gas. So entropy increases. Okay, entropy increases because you're going from solid molecules to gaseous molecules, so there's a greater randomness, so entropy increases. Let's look at enthalpy. Enthalpy, so this is a change of entropy, this is a change of enthalpy. So what does that say? Becomes hot. Becomes hot, that means energy is released, so it's a negative change of enthalpy, so it's an exothermic reaction. So you have got an exothermic reaction, you have got an positive change of entropy. So the positive change of entropy, so the first section, this is looking at this equation. So this is looking at the chemical reaction. This is looking at the system. The system entropy increases. And then when you look at the negative change of enthalpy, because heat is in release, this is looking at the surrounding. This is looking at this entropy of the surrounding. What does that mean? Is that if you have an exothermic reaction, you release heat. Yeah, and where does the heat energy go? The heat energy will be released to the surrounding particles, and then the particles will get more kinetic energy because you have got more heat energy. So when they have more heat energy, you know, let's just write it down. So you release energy, because some of you are visual learners. It release energy, so the surrounding particles move faster because they have more heat energy. They have more kinetic energy as a result of increased heat energy. When they move faster, doesn't that mean it's more random? Like they become more random. They move around, so it's more random. When they're more random, therefore the change of entropy increases. So the surrounding entropy also increases. So you have an entropy increase in the system, you have an entropy increase in the surrounding. Therefore, you know, the overall, if you just add these together, the total amount of entropy will be positive. Therefore, the reaction will be spontaneous. Okay, so this is more of a, and I always draw this table. When you have a negative change of enthalpy and positive change of entropy, you're always going to be spontaneous. If you have a positive change of enthalpy and negative change of entropy, it's never going to be spontaneous. And then if you have one of each, like say you have negative change of entropy, negative change of enthalpy, and then you have positive or both, positive of each one, then this is temperature dependent. Okay, so what that means is that if you have a negative change of enthalpy, that means, yay, we have surrounding entropy increases, but then you have the system's entropy that's decreasing, and then it just depends on which one's bigger, which one is more significant. So if the one that I'm highlighting now, if the change of entropy, the negative change of enthalpy is more significant, then it's going to be spontaneous. Okay, and so in the following case, I have the entropy, positive change of entropy in the system, but then the positive change of enthalpy means the energy is being absorbed. That means the surrounding environment is less random, and then it just may be. So if this one is more, the one I highlighted is more significant, then the system is more the reaction is spontaneous. Okay, so let's just look at more written answer here. So the entropy increases, so the system increases because you're going from solid going to gas, so greater randomness, blah blah blah. And the reaction is exothermic because it's becoming hot. That means heat energy is released, so the surrounding air particles gain kinetic energy, so the surrounding increases. And since both increases, therefore the total amount of entropy increases, therefore the reaction is spontaneous. Okay, so that's that one. Oh, question 3. This is going to be about Lewis acids and bases, not acids, but Lewis diagrams. Yeah. So SPD. So this is just a cheat question. So I'm just going to do the first one full. So this is how many is that? 27 electrons. So 27 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. 27 electrons. For AS, I'm not going to do the first part anymore. I'm just going to do argon. And then 4s2, 3d10, 4p3, Cu2 plus. Now for Cu2 plus, I would like you to do this first. All right. So Cu2 plus is 29 electrons, and copper is 31 electrons. Okay. So what we want you to do, what I want you to do is do the argon, do the copper first. Just do copper. Cu. So this is going to be argon, 4s1, 3d10. And then you need to turn that to Cu2 plus is by losing 2 electrons. The reason why I do this is that you always want to lose the 4s first, and then you lose the 3d. So you're going to lose the 4s1, and then you're going to lose one of the 10. So it's going to be argon 3d9. Okay. Next one, compare the radius. Explain why the radius of magnesium atom and the ion is different. Because you lost electrons. If you got, Mg atom, this is 12 electrons, this is 10 electrons. I mean, you can always do the, I'm not going to bother with that there. You can always write, why don't we do it? 1s2, 2s2, 2p6, 3s2, this is Mg. And Mg2 plus is 1s2, 2s2, 2p6. Okay, so you can see Mg atom is going to be a lot bigger because you have got an extra energy level. So that means there's more repulsion between the energy levels, and therefore the atoms is going to be bigger because the valence electrons are going to be further away. Okay, so they have the same number of protons. So that means the amount of pull from the center of the atom is the same, but then the atom loses 2 electrons to become an ion, and therefore you lost an entire energy level. And when you lose the entire energy level, there's less shielding, there's less repulsion, and therefore you have more stronger force of attraction between the nucleus and the valence electrons, and therefore you would have a stronger force of attraction and then a smaller molecule. Okay, a smaller atom in this case. All right, Lewis diagrams. So BRF3. So first, when you do these electrons first, when you do these Lewis diagrams in level 3, we don't, forget about if you watch my level 2 videos and got some help from there, ignore that method. It doesn't work anymore because the octet has expanded. So the first thing you need to do is that you need to figure out how many electrons you have. So this is 28 electrons. I have 28 electrons because bromine 7, F is 7, there's 3 of them, 4, 7, 28. So just do this first. Do Br, F, and then single bond everything. And then make sure your fluorine has got 8 electrons, and this is where you just count. So this is 8, this is 8, this is 8, 3, 8, 24. I need 28, so it's 24, 26, 28. All right, so this is, I'm just going to draw it like that. It doesn't matter how you draw it really. Well, it does matter, but make sure you don't forget the dots. Okay, so this is T-shape because you got 1, 2, 3, 4, 5 regions, 3 bonded T-shape. PCl6, I'm not even going to bother. When you have 6 things, it's just going to be octahedral because there's nothing else. So when you have 6 atoms being bonded to the center atom, it's just going to be octahedral. All those bloody dots. And don't forget to do your square bracket. Okay, octahedral. Now the reason you need to do a square bracket because that's a negative ion, so do that. Right, the name, blah blah blah, ASF3 and shapes and polarity. Okay, so this is just you know, when you talk about the shapes, you just go, right, so for ASF3, this is 1, 2, 3, 4 regions, so 4 regions of electronegativity, and then one of them is not bonding, 3 bonding, they'll repel each other as they'll position themselves as far as possible to minimize repulsion, and therefore you would have a trigonal pyramid shape. Okay, so like I said here, but then what is ASF3 is going to be polar. Why is that polar? Because the ASF bond is polar because of significant electronegativity difference. All right, so you need to talk about the bond, polar bond, and that results in bond dipoles. All right, yeah, that has bond dipoles, but then the shape, then you relate back to the shape, is asymmetrical, and therefore they can't cancel each other out, hence it's polar. Okay, so for ASF5 it's going to be a little bit different. So again, you got 1, 2, 3, 4, 5 regions, so 5, they're all connected, that's why it's trigonal bipyramid. The ASF bond is polar, but because, and then you create bond dipoles, but then the shape is going to be symmetrical. You have a symmetrical shape, and that means the dipoles cancel each other out, hence it's non-polar. Okay, so the F and AS have significant electronegativity difference, creating polar bonds, but then ASF3 has 4 regions, blah blah, and 3 bonding, 1 lone pair, and they result in a trigonal pyramid shape because they want to maximize repulsion. And then lone pair asymmetrically arranged, the dipoles don't cancel, therefore it's polar. Whereas the other one has 5 bonded, all connected, trigonal bipyramid, they are symmetrically arranged and they cancel each other out, and then it is polar, non-polar. Okay. All right, so it's very standard questions. You can always expect some Lewis diagrams and shapes questions. It's just always how it is. No surprises really. Now let's have a look at next one, last one I think it is. Write the equation. Oh, is this Hess's law? No, there's no Hess's law questions in this exam. Oh damn, oh, that's a bummer. All right, write the equation to show the reaction that has an enthalpy change equal to, so this is where, just on a side note, this is where I would highly recommend you to do more than 3-4 years of examination paper if you were to sit the NAV exams, because you get to see a huge variation of questions. You can see how this year there was no Hess's law, maybe in 2019 there were some Hess's law, and then maybe this year there will be some Hess's law again. So, you know, it just, once you've seen all the variations, you will do quite well. All right, let's do this one. What are we doing here? Ionization energy. So ionization energy is the amount of energy required to remove 1 electron from 1 mole of the atom at gaseous state. So that means you lose 1 electron from 1 mole of atom at gaseous state to make the positive ion. All right, justify the difference in the ionization energy for nitrogen, potassium, and arsenic. If you look at the periodic table, let me quickly, should I find it for you? Periodic table of elements. So you have nitrogen, you have K, which is over here, and then you have nitrogen, which is over here, and then you have arsenic, which is over here. Okay, so this is group 1, this is group 15, this is period 2, this is period 4. Okay, so there's something in between, doesn't matter. So you can see N and AS are the same group. Okay, so we know as you go across the periodic table, the radius, the radius decreases because there's more force of attraction on the valence electrons due to this shielding, equal amount of shielding but more protons. Radius decreases, ionization energy increases because it is harder to remove an electron. As you go down the group, the radius decreases, the radius increases, and then the ionization energy decreases because it takes less energy to break them out. So this is why, if you look at this, your ionization energy, your arsenic will be larger, will be the ionization energy will be smaller of AS will be smaller than the nitrogen. Why is that? If you look at this comparison, is because they're in the same group. They have so nitrogen has 7 protons, 7 electrons, and arsenic has way more protons, electrons, but then arsenic has more the electrons in the higher energy level, so there's more shielding. Okay, so valence electrons are being shielded by inner shells because there are more shells, the more energy levels. So these valence electrons are shielded more, therefore they can hide from the protons a little bit better, so they're further away, so it is less easy, so it's more easy for them to escape. Okay, but if you compare K versus arsenic, they're in the same group, same period, the amount of the ionization energy of arsenic will be higher than K, because, you know, as we stated here, as you go from left to right, the ionization energy increases as you go across the periodic table, because they have similar amount of shielding. Okay, they have similar amount of shielding, but then there's more protons as you go from left to right. So there's stronger force of attraction coming from the nucleus. So they're pulled in closer, so it is harder for them to be lost. Okay, so this is pretty much what you talk about every single year for questions like this. All right, so but you do want to always talk about two things. When you talk about these, you want to talk about shielding effect, and you want to talk about the nuclear charge. Okay, so the nuclear charge is from this is the number of protons. You can think of it like that. Okay, so nitrogen and arsenic in the same group. Yeah, so it decreases on the group because the valence electrons are, because there's more shielding, because they're further away. Okay, despite having more protons, so this is why you want to talk about both, because despite having more protons, but because, you know, this effect of repulsion shielding is greater, then, you know, it's not as significant in terms of having more protons. Okay, but then if you compare potassium and arsenic, then in the same period, ionization increases across the period, because they're from the energies are being removed from the same energy level, so the same amount of repulsion, but the number of proton increases. So there's more proton, more stronger force of attraction from the nucleus, therefore it is harder for the valence electrons to escape. Okay, very standard sort of questions. I get really tired doing the questions like this. Very, very not creative, but, you know, that's what they look for in these types of exams. All right, so that's the end of this this particular video. I hope you're finding this helpful. Very predictable examination paper. In terms of difficulty, if you ask me how difficult this is compared to previous exams, it's pretty standard. Other than that heat curve water, because normally there will be a Hess's law question, but they replace it with a heating curve. But other than that, very, very standard exam. So yeah, so hopefully I've helped you to a certain degree, and yeah, so leave a like and subscribe if you haven't, and I'll see you guys next time. Bye bye.